Now the question I will ask now is, how does this density of state change with time? What does the dynamics tell me? You see, this description, I just can take many copies of my system. I just consider them as points in my phase space and then let my system evolve in time. So these points in phase space will just be moving around, and the density in principle can change in time. I'm not necessarily asking this question for an equilibrium system. For an equilibrium system, I will require it to be independent of time. But I can ask this question in general for an arbitrary system. Just take many copies. There will be the density in phase space corresponding to these copies. And I can ask the question, how do they evolve in phase space? How does this density evolve? Now, let me consider some volume in phase space. Let me call that volume omega. Well, there are this many points in that volume omega. I can ask the question, how does this number of points change with time? You see, I'm not creating new copies. Once I create copies, well, the number is fixed. So the only thing that can change is these points are moving around. So the only reason that this many points, the total points in this volume omega might change is if they flow out of this volume or if they flow inside the volume. So this should be equal to J dot, let me say, dA over the boundary. Let me put a minus sign. dA I will be taking to show outside. So the number of points in my volume can change only if there is a flow of points outside or inside my volume. And in fact, I can convert this to a volume integral also. This will be equal to divergence of J dV. Yeah, this is dP dQ. Let me put the explicit time dependence of, possibly explicit time dependence of rho. The right-hand side will be, well, the only time the volume, I'm not looking at a volume that is changing in time, I'm looking at a fixed volume, so the volume doesn't change. The only reason why the number of points in my volume can change is if rho changes. Which basically tells me that d rho by dt plus divergence of J should be equal to 0. Well, this is the famous continuity equation. If you have any conserved quantity, if rho is the density of that conserved quantity and J is the flux of that conserved quantity, this is the statement of conservation. Not just for the ensemble, the points in my ensemble, but I don't know, if you look at charge, electric charge, and charge density, they should satisfy this. Any conserved quantity and density flow should satisfy this equation. Now let's look at J. What is J? And also keep in mind that this divergence is not the three-dimensional divergence. I'm in 6n dimensional phase space, so this divergence is 6n dimensional divergence with respect to each of the coordinates of position and moment. Now, what is J? Well, the current is nothing but the density multiplied by the volume, the velocity. And remember, this is not the velocity in real space. This is the velocity in phase space. This is a 3n dimensional velocity. Or if you like, I can write this as rho qi dot and rho pi dot. I goes from 1 to 3n. Now, if I go back to my continuity equation, d rho by dt plus the divergence of rho and v should be 0. This will be d rho by dt Well, the divergence is nothing but take one component of your vector. For example, I can look at the q components, and then take the derivative with respect to that coordinate. And there are also other components, momentum components. This should be equal to 0. You see, in three space, divergence of any vector was a x, x, a y, y, a z, z. Here in this 6n dimensional space, the components are qi and pi. That is why if I take the qi component of the velocity, it is this one. I'm taking the derivative with respect to qi. The pi component of the velocity is this one. I'm taking the derivative with respect to pi. Now let me take these derivatives explicitly. d rho by dt plus d rho by dqi, qi dot plus rho times dqi dot divided by dqi plus d rho by dpi, pi dot plus rho times dpi dot by dpi. This should be equal to 0.
Why did we change the usual time derivative into a partial derivative?
You see, I was looking at this integral. In principle, that integral can only depend on time t. It doesn't depend on anything else. So if I take the derivative with respect to t, well, that's the total derivative with respect to time. It doesn't have independence on p or q. Now, the time in principle, the time dependence of that integral could have come from two different places. The time dependence of rho and the time dependence of the volume. Well, I might be considering a moving volume. The volume could also be changing. But the volume doesn't change. I'm not looking at such a case. I'm looking at a fixed volume. So if I move the time dependence inside, this derivative is actually the derivative with respect to this time only, not with respect to p or q. That is why when I take the time derivative inside the integral, it's not taking the derivative with respect to p or q, it's taking the derivative with respect to t only. And hence it becomes the partial derivative of rho. So I don't have p of t or q of t over there. P and q doesn't depend on time. Because p and q, they just denote points in phase space, not the location of a particle evolving in time. That is why I'm not taking the time derivative of p or q. Okay, have you taken analytical mechanics? Do you remember what you have learned over there? These ones, pi dot is equal to qi dot is equal to, in terms of Hamiltonian, what are the Hamiltonian's equations of motion?
I think pi dot was minus del h over del qi, and the other one was del h over del pi.
Well, if you have trouble remembering which one was minus, which one was positive, you can just imagine a very simple Hamiltonian. So q dot is p over m. This is dh by dt. So this is positive. The first one is negative. Well, let me look at this qi, derivative of qi dot with respect to qi. That kind of looks the weirdest derivative here. This is equal to del over del qi dot is del h over del pi, but second derivatives of nice functions, I can change their order. This is equal to derivative with respect to pi of derivative of the Hamiltonian with respect to qi. Well, this is just minus pi So this is minus the pi dot, minus the derivative of pi dot with respect to pi. So this term and this term, they cancel. They are just minus, one is the minus of the other one. I'm left with the other two terms, so del rho by del t plus derivative of rho with respect to qi. Well, qi dot is derivative of the Hamiltonian with respect to pi minus del rho by del pi. Derivative of pi dot is minus the derivative of Hamiltonian with respect to pi, no, qi. This should be equal to 0.
Are the signs right? Don't we go plus?
Okay, so what I have is del rho by del t plus del rho by del qi dot plus del rho by del pi dot. This is equal to 0. Pi dot is minus derivative, so here I have a minus sign. But now let's look at this equation first. Just imagine I'm just following one of my points with time. So then my Hamiltonian, or rho, the density at the position of that point will be given by P of t, rho of P of t, Q of t, and t. I'm just following one point. I'm in my moving frame, I'm moving with my point, and I'm asking how does the density change as I move with my point. So if I take the total derivative, now this function now depends on t only, because p is a function of t, q is a function of t, there might be explicit t dependence also. Then I can ask the question, what is the total time derivative? It is this one. So how do you take the total time derivative? Well, you take the derivative of rho with respect to p, then take the time derivative of p with respect to t, it is this one, and then take the derivative of rho with respect to q and the derivative of q with respect to t, it's this term, and the time derivative with respect to the explicit time dependence. So this basically tells me that the density of states, the density in phase space doesn't change in a moving reference frame. You see, this is independent of whether you are looking at an equilibrium system or not. This is valid for any system that you study in phase space. We haven't made any assumption about the equilibrium property. The only thing we assumed was that my system satisfies Newtonian dynamics. Well, let's look at the second line now. This is d rho by dt. Does the other two terms remind you of anything? It's the Poisson bracket in classical mechanics. So it's the Poisson bracket of rho with h. This should be equal to 0. Well, in equilibrium, now we are imposing the condition of equilibrium. Well, equilibrium tells me that my system shouldn't change with time. This should be 0. Because if this is not 0, the averages or the measurements will be changing in time. And hence, in equilibrium, we have the Poisson bracket of this density in phase space should commute with the Hamiltonian should be 0. Well, when we do quantum mechanical treatment, quantum statistics, this will just become the commutator of this density with the Hamiltonian, and it should be 0. Well, this tells me that rho should be a conserved quantity in equilibrium. The general solution will be rho can be a function of the Hamiltonian itself, or the energy. If you like, it can be a function of the momentum, the total momentum of my system, or the total angular momentum of my system. Because the total momentum and the total angular momentum themselves they are also conserved quantities. Or let me also add the n. The number of particles if the number is conserved. So this is the most general dependence. Well, we will see what these are. Any questions here? Now let me ask a question. Let's say that I have one system. I have two systems, and they each have densities in phase space. And the first one is rho 1, the second one is rho 2. What do you think will be the density of this combined system in the combined phase space? You see, if the first one has n1 particles, the second one has n2 particles, the phase space of the first one will be 3n-dimensional, 6n-dimensional, the second one will also be 6n1, 6n2-dimensional. The total system will have a 6n1 plus n2-dimensional phase space. Any guesses?
Weighted average. Weighted average of these four.
Not really. It's kind of if you can also treat these densities as kind of probabilities. Rho will be just rho 1 times rho 2. Just the product. Yeah, that if you also imagine, let's say that you are creating an ensemble. Let's say that you are creating n1 copies of the first one and 2 copies of the second one. For the combined system to be described, to be able to describe the same system, you will have to make n1 times n2 copies. So that all possible combinations will be there. But this tells me that logarithm of rho is logarithm of rho 1 plus logarithm of rho 2. We had seen that rho can be a function of conserved quantities. You can have many conserved quantities, not just restricted to these ones. But it's not just a function of conserved quantities, it's a additive conserved quantity. Now, additive conserved quantities, their number is quite limited. We only have energy, linear momentum, angular momentum, and the total number of particles. So, in fact, logarithm of rho can be some constant minus beta times h plus alpha times n plus beta times p plus gamma times L. This is the most general form. And in fact, you can always go to a reference frame in which the linear momentum is 0, the angular momentum is 0. For these, we can just throw them away. We will be looking at our systems which are at rest and they are not rotating. This is the most general form of logarithm of rho. Now, let's go back to our discussions. Let's relate this to our discussions. The canonical ensemble. You see, what we mean by the canonical ensemble, we make copies of our system all having the same energy. But then logarithm of rho is itself a constant. Well, what is the density? What's rho? Well, density at a given point will be proportional to, let's say, 1 over omega, the total number of states. Now, what about entropy? Where is entropy here? Now, we will define the entropy. Now, whatever system we have, the entropy will be defined as, let me say, pi logarithm of pi, with a minus sign. I'm kind of jumping ahead of myself, but so this is pi is the probability that the system will be in the ith microstate. If you want to relate this to densities, you see rho of I, pi will be, well, rho of I divided by the integral of rho of I. The denominator is all microstates, the numerator is the number of copies you have in the ith microstate.
This definition is different from, because we defined entropy in terms of logarithm of omega previously.
Well, the probability, well, let me just do one more thing and then answer your question. Now, from this perspective, this is called the Shannon's entropy. Mainly from information theory, or the Shannon basically took it from statistics. Now, let me ask the question. What is the maximum value of S? What should be pi so that S is maximized, keeping in mind that sum of pi should be constant? Sum of pi should be 1. Well, this is a maximization problem with constraint. And for such problems, you use what is called the Lagrange multipliers. You see, in general, what you do is, if you want to maximize your functions, you look at the variation of your function as you change the parameters, and you equate this to 0. But the constraint kind of restricts you. It says that you cannot independently change all the variables. There should be a relation between them so that your constraint is satisfied. To get rid of that constraint, what you usually do is you just add this Lagrange multiplier, pi minus 1. Well, if the constraint is satisfied, then I'm just basically adding 0 to my function. Once I add this Lagrange multiplier, I will treat all the pi to be independent of each other. And I will choose alpha such that my constraint is satisfied. Basically, I'm adding one more degree of freedom to my problem. And that additional, so that my variables are independent of each other now, and I choose that single variable so that my constraint will be satisfied.
Well, I'm sure what we said, energy is fixed, but in canonical ensemble, energy is not fixed.
Sorry, microcanonical ensemble. Well, let's see. This is equal to minus the change in pi times logarithm of pi plus pi times the change in pi divided by pi. This is the variation of S as I change the values of pi. Plus alpha, the variation in pi, this should be 0. Or if I combine everything and take into the variation in pi parentheses, what I have is minus logarithm of pi minus 1 plus alpha should be equal to 0, or logarithm of pi should be alpha minus 1. Pi should be e to the power alpha minus 1. What is alpha? Well, I have this constraint. Sum over all microstates pi, this is e to the power alpha minus 1 of sum over all the microstates that my system can be in. Well, this is what we call omega of e the number of microstates, I'm already fixed the energy. So this should be 1, which tells me that e to power alpha minus 1 is just 1 over omega e, but this is just the pi. Now what is the entropy? Well, we already have the expression of the entropy. Sum over omega e. Logarithm is minus the logarithm of omega e. Sorry. Pi is 1 over omega e. Sum over all microstates. Well, these are all constants. This is just logarithm of omega e. Well, if you like, let me add. But this is just 1. So this expression of entropy is the expression that maximizes this Shannon's entropy with the constraint that I have the energy is fixed and the total number is fixed energy. I'm just looking at copies with a given energy.
And the previous one we derived with the Boltzmann factor was for?
Well, this is also with the Boltzmann factor. Well, before we just said, okay, there is this number of microstates. It behaves, its derivative, if you take the logarithm, its derivatives behaves like the entropy. So let's just define it, identify it with the entropy. So that was what we had then. Here in this derivation, I basically said that this is the definition of the entropy. Well, this is from information theory. If you want to relate it to thermodynamics, just divide by the Boltzmann factor.
What was the purpose of adding Lagrange multiplied at first sight?
You see, now we have converted to kind of a mathematics problem, saying that there is this function which depends on these PIs, whose values I don't know. But I'm asking you to find the possible values of PI that will maximize that function. But PIs cannot be arbitrary. The sum of PI has to be 1. So I'm kind of, I'm looking at a maximization problem with a constraint. Now, we use Lagrange multipliers for such problems. What we do is we just add the constraint to our function. So my function is S. This is the function I would like to maximize. This is my constraint. I just add my constraint to my function, multiplying it with some number.
Just to follow the constraints.
Yeah, to impose the constraint.
More.
Then I just look at this variation, assuming that I can change PIs independent of each other. You see, the constraint tells me that this should be 0. Not all the variations of PI are independent of each other. At least one of them depends on the variation of the other ones. But if I want to go from here to here, I have to assume that delta PI is 0. Delta PIs are independent of each other. In fact, what I'm actually doing is, okay, there is one PI that depends on all the rest, one PI whose variation depends on all the rest. I'm saying that, okay, let me choose alpha such that that PI doesn't appear in this equation. So since that PI doesn't appear in that equation, all the PIs appearing in that equation are now independent of each other, and hence, since this sum is 0, independent of which delta PI you choose, the coefficients of each one of them separately should be 0. Any questions? Let's look at the harmonic oscillator.
So in the end, we found out that Q distribution is the one that
Maximizes the entropy. So the probability has to be constant, well, which if you interpret it in terms of the density should be constant in phase space. And the density should be proportional to 1 over the total number of total volume you have. 1 over the number of microstates you have. Well, if you remember our classical description, that number of microstates was given by the area in phase space. So 1 over area is, or the volume, 1 over the volume is basically gives us the constant density in phase space. That's the density of the ensemble. The proportionality constant depends on how many copies you have. But if you just normalize it to be 1, then here we have an equality. If you normalize rho to 1, then you have a probability, not the density. Any questions? Well, let's look at the harmonic oscillator. For simplicity, let's look at the one-dimensional harmonic oscillator. Now, this is kind of a simple system. The Hamiltonian will be given by p squared over 2m plus 1 over 2m omega squared q squared. Well, let me just write this as 1 over 2 p squared plus 1 over 2 q squared. Just change the normalizations and you will have 1 over 2 p squared and 1 over 2 q squared. In PQ phase space, the trajectories for a given energy will basically be, well, if you didn't scale, if you use this expression, they will be ellipses. If you scale them, there will be just circles. Now, you see, in phase space, the point in the microcanonical ensemble, the points that I choose, they are not just distributed over all available phase space, but they are only on the regions in phase space which are consistent with my constraints. You see, in microcanonical ensemble, I have a constraint. I'm saying that the total energy is E. So here, I'm saying that 1 over 2 p squared plus 1 over 2 q squared is equal to E. So although I said that rho is constant in microcanonical ensemble, well, it is constant in the available phase space to my system. But it's not constant throughout the phase space. It is 0 here, it's 0 here, but it's constant on that line. Now, let me also, before continuing with the harmonic oscillator, let me also talk about the ergodic hypothesis. Yes, I said that the density in phase space is constant. But let me look at a different problem, not just a simple harmonic oscillator, but an oscillator with double minima. This is the potential. Let's look at such a potential. And let's say that my energy is over here. Well, if my energy is over there, and if initially my system is somewhere over here, my system will never travel through all the available phase space consistent with the energy constraint. You see, this particle will never go to this point over there. Its energy is not enough. So if you study such a system, and if you say that, okay, in phase space, my available volume is here and here, and the density is uniform, well, it won't be able to describe your system. Because depending on whether your system is initially created on the left or on the right, your system will always remain there. So this is a system which violates the ergodic principle. Which basically states that the system approaches arbitrarily closely to every point in phase space consistent with the constraint of the system. Here, by constraint, I will be talking about mainly the macro state. You see this double well potential. If you study that system, at least at low energies, it will not satisfy the ergodic principle. At high energies, it will still satisfy the ergodic principle, but not at low energies. Any questions? Yes.
Are you still talking about multi-particle systems?
Yes.
If not, well, tunneling.
Well, we are looking at classical systems. Tunneling, you are right. Well, you see, even with tunneling, you see the probability that your system will tunnel from left to right will decay exponentially with the energy. If the energy is low enough for tunneling, you have to wait almost longer than the age of the universe. And then we are back to our discussions about what do we mean by equilibrium. Typically, your system has some relaxation time, and if you wait long enough, the Earth will reach equilibrium, we will be all dead. But so this Earth is not in equilibrium compared to the day, but this room is in equilibrium if we just look at it for a couple of minutes.
We haven't placed any constraint on E over N, right? For this.
Where? Ergodic principle.
Right, yeah.
No, ergodic principle is quite a general assumption that we are actually making. Because we will be imposing only the condition that the total energy is E, the total number of particles is equal to this much. Those will be the conditions we impose, and then we will assume that our ensemble contains representatives sufficiently close to every possible microstate of my system, consistent with these constraints. In this double well potential, well, I also have to, if you want, you can impose whether your system is on the left or on the right as a condition, but that's not our macro state.
In the quantum mechanical case, though, we should have tunneling should follow up with 1 over root N as well, right?
Yes.
I mean, the larger the system, the less likely you should be to. But you're saying that the only constraint here is.
But you see, what is 1 over root N is the probability that all of them will tunnel.
Right.
But if I would be studying a system with a double well potential with tunneling. Well, I would still say that even if N is very large, the ergodic principle will be satisfied if you wait longer than the tunneling time, which doesn't, tunneling time for a single particle, which will not decrease as 1 over square root N.
Right, it will be independent of system.
Yeah, because the system, as the system evolves, some particles will tunnel this way, some particles will tunnel the other way.
In the previous class, we said that we have fluctuations. What if our particle has energy close to the barrier, but below the barrier?
Okay,
as a result
one,
of
we are not looking at fluctuations yet. We will come to fluctuations. Two, we are not studying this problem in detail. Well, of course, I mean, if you are somewhere over here, what will happen will be, well, the ergodic principle will hold because the tunneling time will be very small. The tunneling probability will be close to 1. I'm not looking at a single particle, so since I have 10 to the power 22 particles, they will be basically distributed throughout this volume. I won't expect fluctuations. Unless you start with all your system to be on the left-hand side and see how it will evolve. But once the equilibrium is reached, well, there won't be any I won't expect any fluctuations in the number of particles on the left or on the right.
So if we impose a left-right choice in the beginning, we should get a diffusion equation, right? Or
Well, probably.
like a PD with.
You see, in this course, My concern is not the double well potential. My concern, the reason why I talk about this example is to say that, okay, we are implicitly assuming the ergodic principle, but it doesn't have to hold all the time. There are cases where it will not hold. That's the point, not the double well potential.
Hocam peki what's the rare event and its relation with
What's the?
ergodicity? Rare events.
What do you mean by rare events?
I mean, like I said, somehow a particle have an unexpected energy due to the fluctuations or something.
Okay. So
And it passes across the barrier.
okay. Yeah, you see, quantum mechanically, if you are very close to the barrier, well, already tunneling probability is almost 1. So I will just skip this double well problem. Now, it might be interesting. I don't know if it has been studied in detail in terms of fluctuations, etc., but I didn't study it. Now let's go back to the harmonic oscillator. And let's also, well, in our last few minutes, let's look at this omega zero factor for the harmonic oscillator. You see, omega will be dp dq divided by omega zero. With the well, let me see, sigma of E. And in fact, let me just use this expression for the Hamiltonian. So what is that integral? dp dq integral for this constraint.
You know this?
Sure. You see, this is the you are just integrating. You are looking at the area of the ellipse. I do expect you to know these. And the ellipse is P and Q. This is my ellipse. This point is square root of 2me. This point over here is square root of 2e over m omega squared. So what is the area? Hmm? Yeah, I mean, the area of a circle is pi r squared. Well, circle is just an ellipse with equals major and minor axes. So for an ellipse, it's just the pi times the product of the major and the minor radii. Well, these m's will cancel. I have 2 pi e over omega. The number of microstates in this case will be sigma e plus some delta e over 2 minus sigma e minus delta e over 2, or this will be equal to 2 pi over omega times delta E. And for the harmonic oscillators, if you look at the quantum mechanical system, energy is h bar omega n plus 1 over 2. So for each n, there is an energy. For that n, there is a corresponding ellipse with changing radii. And if you choose delta E to be h bar omega, omega E should be 1. Within an energy range of h bar omega, there is just a single state. Well, that tells me that 2 pi over omega times h bar omega is 1. Here there is also an omega 0. Now the omegas cancel, and omega 0 is 2 pi h bar. We have the same factor for the one-dimensional harmonic oscillator. Since this is one-dimensional harmonic oscillator, we have a to the power 1. If it was a three-dimensional harmonic oscillator, it would have been cubed. For the free ideal gas, for the free particle ideal gas, just particle moving with kinetic energies, we still have omega 0 is 2 pi h bar to the whatever dimension you have for each particle. And in fact, it will be general whatever the potential is. Okay, any last minute questions? So what about the density? No, I will leave it to you. Well, you see, before we looked at the 6n-dimensional case, well, what about the velocity vector over here in this two-dimensional phase space? What can you say about the density, etc.? Let's practice. Any last questions? So in that case, see you on Monday at 3:40.